Hello, this is the third video in my EMG series. In this video, I'm just going to go over the circuits that comprise the front end and show you the results. Well, before I get into it, I guess I'll just remind you of some of the rules I have when choosing components. There's probably, I know there's better components out there, but I mean, the factor that influenced my decisions the most was the cost. Just keep that in mind further along. As a reminder, this is the block diagram from my first video. The first stage is an instrumentation amplifier. It then goes to a high-pass filter and also a gain stage. I guess it's not included in there. Then it goes to a low-pass filter, a rectifier, and finally the ADC. I didn't really test out or make software for the ADC yet. I'm just kind of, I'm lazy. I'm not a software person, I don't think, but I guess I kind of have to be, but oh well, I'll do it later. Okay, I guess I'll just jump right into it. So the connector that I used to actually connect the electrodes to the board itself was another JST connector. It actually turned out to be pretty big, like bigger than I thought. I guess I just didn't read the measurements right, but oh well. The connector being big doesn't really affect anything. Not really. Like later on, I'll probably, in another revision, I'll just put a smaller one on. It really doesn't matter. In any case, here's the front end. I guess I kind of lied when I said that the first stage was an instrumentation amplifier. So in the schematic, the first stage was actually just like a JFET buffer, and that's because I wanted to. JFETs have an extremely high input impedance, and I wanted to just see if it'd be better to have like a very high. I think it's like, I don't know, it's really big. Here's the number on the screen. But as you can see here, I also put a kind of a safety net in, as in these like 0 ohm resistors. So basically, I just, if the JFET didn't work out, I could just reroute the signals to the instrumentation amplifier. And in the end, it did not work out because I put the wrong footprint on the board. Like, it didn't fit. So yeah, make sure you check your footprints, all of them. I was just kind of like, I don't know what happened. I thought I did check it, but I guess I just missed it. Oh well. It's good that it's like not a fatal error. So I made a couple of those. I made another big one later on, which is pretty bad, but this is kind of a tangent, but I've seen microchip parts, like microchip op amps specifically, always seem to have an extremely high input impedance. Like bigger than the others, and I don't really know why that is. Maybe they do something differently. And just to get this out of the way, I also have a 4.7 microfarad and 0.1 microfarad bypass caps. It's just to get rid of the high frequency, like the very high frequency, spikes, if there is any, on the switching power supplies. Yeah, I guess in terms of boards, like this is kind of the only thing I know about making a board is put them as close to the input pins as possible. But other than that, like, I don't know, boards, it's just like, it's honestly to me just like connecting the dots, making it work. Which I guess another thing I don't really know, but in some of these I put the bypass caps on the back side, like just right under the input pin. I don't really know if that's good or not, because it technically is close, but I don't know if a via would have a higher parasitic inductance than just a trace. I've got like no idea. So anyway, for the instrumentation amplifier, the circuit is very easy. You pretty much just need R7 between them. the two 10Ks, I think they just mitigate the effects of like ESD or something. Like if there's a high electrostatic discharge on the lines before that, it'll just like reduce it significantly. I'm pretty sure that's what it does. Yeah, that's what the datasheet says. But in any case, yeah, so the R7 sets the gain. The formula is here, and I chose the gain to be around this value. I don't think I should see a problem with the, a high DC offset from the electrode mismatch. I don't really know until I test it really with the electrodes themselves. But yeah, choosing that gain just gives you a higher common mode rejection. Usually when I make some sort of filter or amplifier type thing, I like to test each stage individually. And since there's so few blocks, it's pretty easy to do so. So the first thing I did was tie the inverting input to ground. So that means anything I put on the non-inverting input would just be passed through because it's taking the difference between them. The other thing I did was change the gain resistor on the instrumentation amplifier to around 3.3K, just so that you can use lower amplitude waves on your input. So then I fed in a 20 millivolts peak-to-peak sine wave and just recorded the output. So as you can see, if you take the output peak-to-peak amplitude and divide it by the input peak-to-peak amplitude, you get a gain of around 28. It's 27, but it's close enough. So the output also shows the problem of electrode bias mismatch. The input sine wave was centered around 0, but the output is around some negative value. There was a DC mismatch between the two pins, and that mismatch was amplified into the output signal. So if you have a really high gain on your instrumentation amplifier, you can end up saturating it because of the DC mismatch. Right after the instrumentation amplifier is the high pass filter. That's actually to remove the DC offset that was amplified by it. Yeah, I mean, I'm not really, unless like the DC offset is like pretty big, I don't think the high gain on the instrumentation amplifier would be bad. But in any case, so this cutoff frequency is around 30 hertz, I think. I used this tool from Analog Devices, which basically just designs a circuit to keep the the damping ratio between like 0.72 or like √2/2. I forget all the stuff from like the filter theory and design, so like I just listen to Analog Devices. I'm sure they're fine. Right after that is a non-inverting gain stage, but the first one, I put a potentiometer instead of like a fixed resistor, and that's just to adjust the gain, because you know, if you have, depending on the person, you could have really dry skin, you need more gain, stuff like that, or just depending on the situation. Like if you have really low signal, you might want more gain. At the low pass filter, there was a problem. The waveform was pretty distorted. After playing around with some components, the values that end up working are changing R8 to 200 ohms, R9 to 3.74 ohms, C11 to 1 microfarad, and C12 to 0.1 microfarad. I think what the problem was that the values of the resistors were too high. So I think the signal at the inverting node was messed up, and so it couldn't properly amplify the signal. In the end, replacing those values worked. As you can see here, the output is fine, not distorted at all. Okay, so after that, I decided to test the frequency response of the entire filter. So I don't have any fancy equipment, so I just injected a signal like I did before, but just varied the frequency and recorded the output gain versus the input gain. And initially, I got this really terrible response. As you can see here, there's just a massive spike, and there are two things that I figured out that was wrong with it. So I guess the first thing is to pay attention in your filter design classes, because this is a topic that they address, and that is the damping ratio. So I found this really good tutorial online, but the damping ratio determines the, I guess you could say, spike at the cutoff frequency. So if you have a really low damping ratio, you have a big spike. It goes above, it actually amplifies your signal. If you have a really high one, it goes below. The damping ratio in mine was really low, and it was causing this huge spike. The other thing was I designed the circuit wrong. The R10 and R11 should be in different spots. Usually you have the higher resistor connected to ground in the non-inverting node. Anyways, after playing around with some values, I kept the capacitors the same, but changed R10 to 21.1K and R11 to 10K. And this was the resulting frequency response. If you remember what I mentioned before, being that most of the information from the EMG signal is in the 50 to 150 hertz region, this filter works pretty well because there's not much variance in the gains in that region. There might be a bit of error from the non-idealities of the filter in the other regions, like the lower end and higher end frequencies, but it's just a sacrifice I'm willing to make. Anyways, after that was all done, I decided to just test out the functionality. So I hooked up electrodes to my biceps. So there was one neutral one on the lateral surface, so near the bone. I think it's like the humerus or something. And then I placed the other two electrodes that go to the instrumentation amplifier around an inch apart on my bicep. And then I just tried flexing it. And as you can see, it is collecting the EMG signal. I'm pretty confident in that. So that's really good. The gain stage is set to the maximum gain. I guess I cranked it all the way just to see what happened. But the signal's still pretty low, but oh well, it still works. So that's really good. I'm not saying that this is like the best possible signal. In order to evaluate the the signal to noise ratio, I'd have to do some sort of like digital signal processing or type thing, and I don't really want to do that, but I can pretty much say with a good amount of confidence that I am collecting the EMG signal. It's not just noise. In any case, that's it for this video. Ciao.